Hello. Now we'll see the Fermi energy, their concept Fermi level and Fermi energy. Fermi energy in conductors is different than Fermi energy in semiconductor. Now in today's topic we'll see the Fermi energy in a conductor. So the Fermi energy in a conductor is the concept which is, in short, we can see how we can uh, obtain the meaning of Fermi energy in a conductor. Then we know in a conductor there are different orbits. The atomic structure we already know in conductor. The nucleus and the electrons are revolving around that nucleus. So there are different states. Depend on that orbital and different state, we know innermost state shell and outermost shell or that corresponding orbits and their energy. Depending on that, we'll define the Fermi energy in conductor as the highest occupied energy level, or we can say highest occupied energy state. So the highest occupied energy level at 0 Kelvin in metal is called Fermi level, and the energy corresponding to it is called Fermi energy. See again, the highest occupied energy level means outermost level. The highest occupied energy level at 0 Kelvin in metal is called Fermi level, and the energy corresponding to that level is called Fermi energy, and that Fermi energy is denoted by letter E suffix F. At 0 Kelvin, all energy state up to Fermi level are occupied and all state above Fermi level are empty. This is in metal. At 0 Kelvin, all energy state up to Fermi level are occupied and all state above the Fermi level are empty. Thus, for conductor or metals, the highest field energy level in highest energy band at 0 Kelvin is Fermi level, and its corresponding energy is Fermi energy. This that's the definition. It is right. I am again repeating that. Thus, for conductors or metals, the highest field energy level in the highest energy band at 0 Kelvin is Fermi level, and its corresponding energy is Fermi energy, which is E suffix F. Now, the exact position of any electron is not definite. We could not give the exact position of that electron or any particle. But to get this idea, we use probability, and there's Fermi-Dirac distribution function. These Fermi-Dirac distribution function give the probability of finding the particle at given energy state. It is probability, but it not give exact position or exact count, but here the approximation. So this Fermi Dirac distribution function is the Fermi Dirac distribution function f of e gives the probability that the energy state E will be occupied by electron at temperature T. That is, this f of E gives the probability of that particular energy state. Means I am repeating this. The Fermi-Dirac distribution function f of E gives the probability that the energy state E will be occupied by electron at temperature T. See here we have written the function f of E. So it is probability of energy state E. If instead of E, if we write f of E1, so that time this probability of finding electrons at energy level E1. If E2, then it gives a probability of finding particle at energy level E2. These Fermi-Dirac distribution function is derived as f of E is equal to 1 upon 1 plus e raised to e minus ef upon kt. I am repeating again, f of E is equal to 1 upon 1 plus e raised to e minus ef upon kt. Now we'll see meaning of each term or symbols in this equation. So where f of E, this f of E is Fermi-Dirac distribution function. Sometimes it is also known as Fermi-Dirac probability distribution function also. So this is about f of E. Next, E. This E, dz, or we can say dz. This E is the energy of eigenstate to be occupied. Means that distribution function is applied to that particular energy state, that is E. Then E suffix f, this E suffix f is, what is this? E suffix f, E suffix x is Fermi energy. Next is a T, this T is temperature, and these temperature, in such cases we consider temperature in Kelvin. And finally remain is K, this K, and the K is Boltzmann's constant. Now depending on these equation, see this, that equation again, f of E is equal to 1 upon 1 plus e raised to e minus ef upon kt. This is Fermi-Dirac distribution function. From these function there are three cases arises. That three cases we'll see. The first case, at T is equal to 0 Kelvin for E is less than EF, means energy is less than Fermi energy. So that is for energy level locate Fermi energy level. So that time what is the probability of finding the particle at temperature 0 Kelvin and energy below the Fermi energy? First we'll see again that wave function, that function, this Fermi-Dirac probability distribution function, which is 1 upon 1 plus e raised to e minus ef upon kt. Now when energy level below the Fermi energy level, then that time the quantity e minus ef in equation is negative, and the argument of exponential function will be minus infinity. See this, as E is less than EF, so that time these difference will be negative, and the value of T is 0. So that negative term divided by 0, that time it becomes minus infinity. So the minus infinity, the value, so wave function we can write f of e is equal to this 1 upon 1 plus e raised to minus infinity, and we already know e raised to minus infinity is 0. So it becomes 1 upon 1 plus 0. So it gives 1 upon 1, that is 1. Or we can say there is probability of finding electron in this energy state is 1. 1 means it is 100%. So we can conclude it f of E is equal to 1 implies that all the levels below Fermi level are occupied by electron, and there is 100% chance to find electron in that energy state. Next case, at T is equal to 0 Kelvin and E is greater than EF. Energy level greater than EF, that is Fermi level. So it means for the energy level locate above the Fermi energy. Energy level above the Fermi energy. In that case, what will be happen about the probability? So first, again see first Fermi Dirac probability distribution function is f of E is equal to 1 upon 1 plus E minus EF upon kT, and when energy level is greater than EF, the quantity E minus EF is positive. See, as this E is greater than EF, so this difference will be a positive, and the argument of exponential function is infinity, cause these t is 0. When t is equal to 0, so the positive number divided by 0. Any positive number divided by 0, that time uh, the calculation gives to infinity, and this infinity is plus infinity. So these function gives 1 upon 1 plus e raised to plus infinity. So we can see that step. Thus f of e is equal to 1 upon 1 plus e raised to infinity, and e raised to infinity is infinity. So 1 plus infinity will be again infinity, and 1 upon infinity gives to 0. So it gives 0% chance to find electron in that energy state. So we can conclude as f of E is 0 implies that all the levels below Fermi level are vacant. That means there is no scope to find electron at energy level above the Fermi level, and cause which is vacant. Third case, at T is greater than 0 Kelvin, and for energy level is equal to Fermi level. I am repeating it. Temperature greater than 0 Kelvin and energy level is equal to Fermi level. That means energy level equal to Fermi energy, and temperature is greater than 0 Kelvin. So again see the Fermi Dirac probability distribution function f of E 1 upon 1 plus e raised to e minus ef upon kt. Now in this case e minus ef is equal, so these difference e minus ef becomes 0 and divided by a positive number. So that time this 0 upon positive number, uh, this calculation gives to 0. So it is 1 upon 1 plus e raised to 0, and we know value of this 1, so it gives half. It indicates They implies that probability occupied Fermi level is above